We've now introduced the independent t-test, which is concerned with comparisons of independent groups. You'll recall that independent groups are groups that do not share any characteristics in common. They are uncorrelated. But what about situations in which there is a purposeful correlation between groups? What do we do when, for example, we're working with a repeated measures analysis? This video is concerned with mean comparisons between correlated or dependent groups. You'll recall that independent groups are groups that do not share any characteristics in common. They are uncorrelated. There are, however, lots of scenarios in which there is a bona fide correlation between groups. You might have repeated measures, when the same people are tested on 2 occasions. This type of design is quite common in interventional studies when we evaluate the effects of a treatment by looking at outcome measures both before and after a treatment. We might be testing siblings. Obviously, this is not the same as testing the same people twice, but siblings typically share the same home environment, probably have similar school experiences, and in general have a number of characteristics in common. They're definitely correlated. In other words, we can't say that the groups are entirely independent. Designs that involve the testing of siblings employ an implicit form of matching. There are characteristics that link the 2 groups. But we might also explicitly test matched groups in which the individuals are paired according to, for example, age, sex, weight, or academic performance. Regardless, when there is a difference between the groups, when the groups are not independent, we need to take the correlation between groups into account. Before we discuss the mechanics of how we accomplish this, let's explore our motivation for setting up our experiment so that we have dependent groups. Why might we go to the trouble of doing this? The answer, as it turns out, is related to error control. When we set up our groups to be dependent, it's typically because we want to control something called subject variance. To illustrate how this might work in practice, let's consider the following theoretical example. You're interested in identifying the extent to which instructional technique or method might impact on student outcomes in statistics. So, imagine that this sample space represents student performance in a third-year statistics course, as measured by final grades. This circle represents all of the variability associated with student final grades in the course. You might be interested in identifying the extent to which there is an effect of moving the course entirely online, and so you might be interested in evaluating the extent to which there is a difference between a group of students that study entirely online and a group of students that study entirely in the classroom. If we assume that the course difficulty, i.e. the course level and the assignment complexity, is consistent between the 2 groups, then the overlap between the variability in final grade and course mode represents the extent to which there is a difference between the 2 groups because of course mode. Said another way, this area represents the variance in final grade, our dependent variable, that is predicted by course mode, the grouping variable, and our independent variable. This arrangement of variables, one independent variable and one dependent variable, represents the situation that we describe testing within the independent groups t-test. And the area that is common between the final grade and course mode is the squared point by serial correlation that we discussed as a common language effect size estimate within that discussion. But is course mode likely to be the only predictor of final grade? Isn't it also likely that there are other factors that might predict final grade? For example, consider academic ability. If you had an overall average for your students across other courses, this might be useful as a method for predicting how well a student might be expected to do in the course, all things being equal. In other words, it's reasonable to imagine that there would be a correlation between academic ability and final grade in the statistics course. It's also reasonable to expect that academic ability might be related to a student's ability to adjust to an online learning environment. In other words, it's reasonable to imagine that there would be a correlation between academic ability and course mode. Now we can put all that together. We're interested in describing effects on student performance within their final grade in a third-year statistics course. In particular, we are interested in the extent to which course mode, i.e. online instruction versus in-person instruction, predicts a student's final grade. We know, however, that final grade is also impacted by other factors, most notably academic ability. If we can somehow control for baseline academic ability, this will allow us to reduce the amount of error in our model. As you can see in this diagram, there are three regions of interest. Firstly, consider this area, the variance in final grade that is uniquely predicted by course mode. If you were removing the effects of academic ability entirely from our model, you might remove this area from consideration in the model. This particular type of analysis is called a partial regression or partial correlation, and it's well beyond the scope of this course, and it's not really what we set out to do. We wanted to see whether or not there is an effect of online instruction on final grade, and this includes the effects of online instruction across all ability levels. What we really want to do is remove all of the impacts of academic ability on final grade that are not related to our independent variable, which means that we need to remove this area right here. We can frame this error as being random or systematic. Random error is all of the variability in final grades that is not due to a specific cause. Before we controlled for academic ability, we were comparing our treatment effect, i.e. the difference between the means of our two groups, against random error that incorporated all of the variability in final grades that was not related to treatment effect. When we introduced control over variability associated with academic ability, we introduce a source of systematic error to the analysis, that overlap between academic ability and final grade that is not related to our treatment effect. So intuitively, you can see that introduction of control over systematic error, which we sometimes call subject variance, reduces the amount of random error within our analysis. And because that random error is reduced, our analytic power is increased. Okay, but how exactly do we do this? Let's start with our formula for the independent groups t-test. As we discussed last week, the independent groups t-test requires that the variances of the two groups be homogeneous, and we use this property of the independent groups test to justify pooling the variances between our groups. There is, however, a version of the independent groups t-test that doesn't use pooled variances. This is called Welch's t-test. Note that we take the variances of each group into account. We can use Welch's t-test as a base to take into account the effects of correlations between the two groups. If the experimental design involves repeated measures or matched pairs, then it naturally follows that the n sizes for the two groups must be equal. The dependent groups t-test is sometimes called the paired t-test for this reason. And, as we discussed in the Venn diagrams presented on the previous slides, when there is a correlation between the groups, when there is a dependency between the two groups, we can reduce the random error within our analysis. This has the effect of reducing the denominator of our calculation, shown here as a removal of the covariance between the two groups. In point of fact, this is a more general form of the independent groups t-test. If the covariance value in the denominator of this equation is 0, i.e. when there is no relationship between the groups, then this new component of the equation reduces to 0, leaving you with Welch's t-test, or your standard independent groups t-test if you substitute the pooled variance for each of the two group variances. Returning to the crux of this lesson, however, if there is a correlation between the two groups, and if that correlation is positive, which is what you would expect if you had undertaken some sort of matching design and had attempted to pull out some sort of common source of variation between the two groups, you would see that the denominator would get smaller, which would mean that the dependent groups t-test will be larger than the independent groups t-test whenever there is a positive correlation between the groups. Let's think about what this would look like within the data set. If we have two correlated groups of individuals, we're interested in looking at the difference between the two group means, in the same way that we were interested in the difference between the group means within the independent groups t-test. In the independent groups t-test, however, we compared this between groups difference against the within groups difference, which we identified by looking at the variances for each of the groups. Because the data are presented in pairs, corresponding to either repeated measures or individuals that are arranged in matched pairs, we need to take this pairing into account. The way we do this is by computing a difference score for each of the pairs within our data. This gives us a number of difference scores that take into account the shared variability within each participant for repeated measures, or each pair of matched participants. And this is the data that we will use in our paired t-test formula, which means that this was really a very long walk to illustrating that the dependent groups t-test is calculated using an almost identical formula to what we used in our calculation of the single sample t-test. The numerator of the dependent groups t-test is equal to the mean of the difference scores minus the null hypothesized difference between groups. Fun fact, this mean is exactly equal to the difference between the mean of group 1 and the mean of group 2. The denominator of the dependent groups t-test is equal to the standard deviation of the difference scores divided by the square root of the sample size, or if you prefer, the square root of the variance of the difference scores divided by the sample size. And because we're really comparing the difference scores and not the columns of values, the degrees of freedom for the dependent groups t-test is equal to the number of difference scores minus 1. Because the calculation of the dependent groups t-test is arithmetically identical to the calculation of the single sample t-test, we will calculate our effect size estimates and our confidence interval using very similar equations to what we used in the single sample test. As we did with the single samples test, we can calculate an effect size estimate using either Cohen's d or the squared point biserial. Cohen's d is just the ratio of the average difference score to the standard deviation of the difference scores. The squared point biserial, our common language effect size estimate, can be calculated to be the ratio of t squared to the sum of t squared and the degrees of freedom for the calculation. And finally, we can calculate the confidence interval surrounding the mean difference by taking your point estimate for the difference between the means, i.e. the mean of the difference score vector, plus or minus the bound for that point estimate. This bound is calculated by taking the t-critical that is associated with the amount of confidence that you want to have in your interval, multiplied by the standard error of the difference between the two groups, which is simply the square root of the ratio of the variance of the difference scores to the number of pairs. Note, of course, that the calculation looks the same as the single sample test of means, but this is a confidence interval around the difference between your group means. We've noted that the obtained value of your dependent groups t-test will generally be larger than the independent groups t-test. But is it always more powerful? No. Recall that the increase in power for the dependent groups t-test, as compared with the independent groups t-test, comes from pulling systematic error variance out of your random error variance. But this comes at a cost. The degrees of freedom for the dependent groups t-test is always going to be smaller than the degrees of freedom for the independent groups t-test. Thus, the critical value for the dependent groups t-test is larger than the critical value for the independent groups t-test, owing to the fact that critical values increase as degrees of freedom decrease. So, in order for this error control to produce an improvement in power, you need to be removing enough systematic error variance as to justify your design. Generally speaking, we say that the dependent groups t-test is more powerful than the independent groups t-test whenever we have control for relevant or meaningful confounds. And this is why repeated measures analyses are generally more powerful than matching designs. Repeated measures analyses engage in better control over subject variance. I mean, consider the fact that no one is as correlated with you as you are. Okay, let's take a look at an illustrative example. In this example, you carried out a study to compare the Montreal Cognitive Assessment scores, the MoCA scores, of community-dwelling seniors in urban and rural centers, matching the individuals for age and sex. You want to determine whether or not the individuals living in rural areas have a significantly lower MoCA score than the individuals living in urban areas. This might provide important information as to how this assessment tool has systematic biases that affect the test scores of rural-dwelling seniors, and it could impact on the ways in which we interpret scores on this measure. Given that this is paired data, we need to arrange the data in matching pairs of individuals. Because this is a matched groups design, each row represents pairs of individuals that have been carefully matched by age and sex. The idea here is that we're trying to ensure that there are no MoCA differences between the groups that might be attributable to either age or sex. In step 1, we need to identify our hypothesis statements. Note that I've explicitly specified the ordering of my subtraction in these hypothesis statements. This is a particularly good practice to get into when working with a one-directional hypothesis test, given that the order of subtraction is critical for proper application of the inequality signs within these hypothesis statements. Step number 2, we choose our test, and the test is a dependent samples t-test. It's a dependent samples test because it's a matched groups design. We're matching participants in pairs based on age and sex. In step number 3, we define our rejection region, and to do so, we need to calculate a value for degrees of freedom. We have 30 participants, but they are organized into 15 pairs. Thus, we have 15 minus 1 equals 14 degrees of freedom. Because this is a one-tailed hypothesis test, we only have one rejection region, and so we should not split the alpha. We will reject the null hypothesis when we have a t obtained that is greater than 1.7613. And when we calculate our obtained value of t, we find that it's 1.88. That obtained value of t is greater than our t critical, and so we reject the null hypothesis. We conclude that there is evidence to suggest that MoCA scores are significantly lower among the individuals within your rural dwelling sample. Given that all of the individuals within your sample were given functional assessments within their home, this may suggest that the MoCA has some urban-rural biases that could be explored in future research. But how much lower do the scores tend to be? Well, in order to determine that, we can calculate an effect size estimate. We calculate Cohen's d, and we find that individuals within the rural sample tend to be 0.49 standard deviations lower than individuals within the urban sample, and that approximately 20% of the variability in MoCA scores can be predicted by whether the individual lives in a rural or an urban location. Finally, we can also note that we're 90% certain that the score difference will be somewhere between 0.11 and 3.49. Example number 2 is a little different. There's no raw data. What? Actually, this is kind of an important way to think about the analyses that we're learning. It's entirely possible that you might want to check the statistics reported in a peer-reviewed paper to ensure that you agree with the calculations. Given that researchers rarely provide raw data within their papers, although this is changing in the wake of calls for researchers to post raw data in open repositories to facilitate exactly this kind of reanalysis, it's a worthwhile exercise to consider how you might carry out a reanalysis with only summary data at your disposal. I've summarized the data that you were presented here. As a reminder, we don't need to consider n size separately for the pretest and the post-test, given that it's a repeated measures design. The n size is the same in each phase of your study, given that it's the same person being tested on each occasion. One of the questions that you might ask yourself is, why is the correlation between groups only 0.7? I mean, shouldn't this be a perfect correlation? It's exactly the same individuals. Well, no, it doesn't need to be a perfect correlation. Even though you are indeed assessing the same people twice, it's important to remember that there will be errors in the assessment of the responses on this measure, at pretest, at post-test, or at both time periods. Also, it's important to consider the fact that even though they are the same people on both occasions, they are also simultaneously not the same people on both occasions. Every measurement that we take from individuals is a snapshot at a particular point in time. It's very plausible that individuals will have subtle and transient differences in health, cognitive, and even personality domains that could impact on the quality of our measurement. In step 1, we need to specify our hypothesis statements. First of all, we need to attend to the fact that this is a one-tailed hypothesis test, and we're testing the extent to which the post-test is less than the pretest, or the extent to which the pretest is larger than the post-test. There's a new bit of information here, though. The question specified that 5 was a clinically meaningful difference and asked you to test the extent to which your difference was larger than 5. Thus, the null hypothesized difference is not 0 for this question, it's 5. Also, because we don't have the raw data at our disposal, we need to use the conceptual formula for the dependent groups t-test. Fortunately, we have the correlation between groups, and so we can carry out a proper analysis of paired values. In step 3, we define our rejection region, and to do so, we need to calculate a value for degrees of freedom. We have 40 participants measured in a repeated measures design. Thus, we have 40 minus 1 equals 39 degrees of freedom. Because this is a one-tailed hypothesis test, we only have one rejection region, and so we should not split the alpha. We will reject the null hypothesis when we have a t obtained that is greater than 1.6849. There's lots of button presses here, but it's still just formula application. As we discussed earlier in this video, this is very similar to what we would have done with an independent groups t-test, excepting for the fact that we're removing the subject variance from the equation. Another key difference that we should highlight is the fact that we always subtract the value of the null hypothesized difference in the numerator. Normally, this is 0. In this question, however, we wanted to determine whether or not the difference was greater than 5, and so we needed to include 5 in our numerator. Our obtained value of t is 3.75, which is larger than our critical value of t. This suggests that we should reject the null hypothesis and conclude that there is evidence to suggest that the training program has reduced stride time. Moreover, because of the way in which we set up our hypothesis statements, we can conclude that our training program has reduced stride time variability by at least 5%. Cohen's d requires that we divide the mean difference by the standard deviation of the difference between the groups after taking the subject variance into account. Unfortunately, we don't actually have an explicit value for the standard deviation of the difference scores. Or do we? Let's consider the conceptual version of the dependent groups t-test that we've applied to our calculation of t obtained in this question. Check out the denominator. That's the standard error for the dependent groups t-test, which means that we can isolate the variance of the difference scores even though we never had an opportunity to calculate them from raw data. Let's calculate our standard deviation first. The standard deviation is the square root of the sum of the variances less the subject variability. We can estimate the latter by multiplying 2 times the correlation between the groups and then multiplying this by the standard deviation of each of the groups. Applying this within our Cohen's d formula, we derive a Cohen's d of 0.59. Note that we still include the null hypothesized difference in this calculation, and this is because we're interested in describing our differences in terms of its relation to the clinically significant difference. So we would interpret this value as meaning that our difference between groups is 0.59 standard deviations greater than the clinically significant value for stride time variability. We don't, however, need to include the null hypothesized difference in our confidence interval. As we did with confidence intervals applied to questions that looked at simple mean differences, i.e. a difference of 0, we can examine the confidence interval to see if it includes our null hypothesized difference within it, i.e. if we had decided that we don't want or need to carry out a hypothesis test. Let's take a look at example number 3. An experimenter is interested in the effects of providing counseling resources on caregiver stress. To test the extent to which these resources have an impact, she provides 10 individuals with counseling resources and assesses their scores on the ZBI-12 8 weeks later. And the data is shown here. The values in the first column are the scores on the ZBI-12 before the 8-week study period, i.e. the pretest scores, and the values shown in the second column are the ZBI-12 scores that are assessed after the study period. They're the post-test scores. Our next task is to calculate that vector of difference scores. As we've done in the past, we want to try to subtract these scores in an order that gives us a positive value, because positive values tend to be easier to work with throughout the hand calculations. If you look down both columns of numbers, you'll see that the values in the pretest column tend to be larger than the values in the post-test column, and so it's probably a good idea to calculate your difference score as pretest minus post-test. As they say, however, your mileage may vary. After you work through these values, you'll note that you do have a negative score. You might be tempted to take the absolute value, even after my having told you not to on a couple of occasions already. But don't do it. It's a bit weird, though, isn't it? That negative score means that someone in your study actually experienced more burden after receiving the counseling resources. But this happens. Lots of clinical treatments show a similar pattern to the results. This might be an indication that treatment effectiveness varies a bit, or it might just be a reflection of the variability within the samples. Regardless, leave the scores alone. It's important that subtraction be done consistently throughout the calculations. In step number 1, we need to identify our hypothesis statements. Note that I've carefully specified the ordering of my subtraction in these hypothesis statements so that we can interpret our results more easily at the end of the analysis, i.e. positive scores mean that the pretest scores are higher than the post-test scores. In step number 2, we choose our test, and the test is a dependent samples t-test. It's a dependent samples test because it's a repeated measures design. We have 10 participants, and we're evaluating them before and after an intervention. In this way, we are attempting to control as many of the individual differences that might go into predicting caregiver stress as is possible. Step number 3, we need to define our rejection region. We do this by first determining the degrees of freedom for the analysis. Since we have 10 participants in our repeated measures design, that means that we have 10 pairs of data and 9 degrees of freedom. We have an alpha of 0.05, and so the critical value is going to be 2.2622. Remember that we have to split the alpha in this example because it's a non-directional hypothesis. We will reject the null hypothesis whenever the obtained value of t is greater than 2.2622 or less than negative 2.2622. Which, as you can see from this t-obtained calculation, is the case. We generate a t-obtained value of 3.91 when we apply our formula. And so we reject the null hypothesis. And we conclude that there is evidence to suggest that provision of counseling resources may reduce caregiver stress. And looking at our effect size estimates, we can say that caregiver stress is 1.24 standard deviations lower than it was before the intervention. Or we can say that 63% of the variability in caregiver stress at the post-test time period may be attributable to the provision of counseling resources. We can also say that we're 95% confident that provision of counseling resources will reduce caregiver stress by 2.15 to 8.05 points on the ZBI-12. This interval does not contain 0, suggesting that we may conclude that there is a statistically significant difference between the groups within a two-tailed hypothesis test that has an alpha of 0.05.